Welcome to this explainer. If you work with speech-to-text pipelines, you know the absolute headache of transcription errors. They are just the worst. Today, we're unpacking a massive breakthrough that actually fixes them. An elegant new framework called GSPIN. It completely transforms these pipelines by decoupling phonetic reasoning from semantic selection. It's a total game changer, and we're going to break down exactly how it works.
So here's our roadmap for today. We'll cover the hidden ASR threat, traditional correction failures, the GSPIN solution, its three-stage architecture, and finally, a developer deployment guide.
All right, let's dive right into section 1, the hidden ASR threat. Okay, here's a totally fascinating paradox for you. We have these modern ASR systems today that boast ridiculously low overall word error rates, right? The metrics look fantastic on paper. And yet, they are still causing catastrophic failures in downstream natural language understanding, or NLU pipelines. So you gotta ask yourself, how can a system with such great metrics still fail so spectacularly when it comes to actually extracting intent?
Well, the answer lies in something called residual lexical errors. Basically, these are structured mistakes arising from phonetic similarity that somehow survive standard decoding. Think of that kind of like a bad spell checker ignoring the wrong word just because it's technically spelled correctly. The absolutely crucial point here is that these aren't just random blips of noise. They are highly structured deviations that happen simply because words sound similar. They're phonetic mistakes, and they slip right past our traditional error checks.
And here is the real kicker. These residual errors don't just happen anywhere, they aren't uniformly distributed. Instead, they cluster around literally the worst possible places. Semantically critical tokens. We're talking about named entities, negations, and sentiment-bearing words. Think about it. Your overall word error rate might be amazingly low, but if the one word the system mishears is a not, it flips the entire intent classification. A corrupted entity totally breaks your slot-filling pipeline, and a shifted sentiment word entirely corrupts your analysis. Which brings us to section 2, traditional correction failures. Now, traditional correction methods usually rely on two pretty flawed approaches, naive token-level dictionary lookups or unconstrained generative models like LLMs. Naive dictionary lookups fail because they search this huge unconstrained vocabulary space, basically mixing up words that make sense with words that are acoustically impossible. And unconstrained LLMs fail for a similar reason. They absolutely hallucinate. They might spit out a perfectly logical, grammatically correct sentence, but they completely ignore the original audio signal. A true correction absolutely must respect both the language distribution and the acoustic boundaries of what was actually spoken. So let's talk about the fix in section 3, the GSPIN solution.
Enter GSPIN. This is a modular, inference-time framework that leverages graph neural networks, masked language models, and large language models to fix these really stubborn ASR errors. And the big takeaway for you here? It requires absolutely zero model retraining or fine-tuning. None. It functions entirely as a lightweight post-processing layer that you can just slide right into your existing speech-to-text workflows.
So the really brilliant part is how GSPIN actually solves the problem, and it does so through decoupling. GSPIN smartly splits the problem in two. It isolates acoustic plausibility, meaning what does the word actually sound like, from contextual semantics, meaning does this word make sense in the sentence? By uncoupling these two dimensions, the framework ensures that any correction it makes respects the original audio signal, while still fitting perfectly into the context of the conversation. Let's unpack how it does this in section 4, the three-stage architecture. GSPIN follows a very strict pipeline, built to minimize computational cost while maximizing precision. The steps are pretty straightforward. 1. GNN candidate generation. 2. MLM local scoring. And 3. LLM re-ranking. Each stage handles a totally distinct dimension of the error, which, prevents that cross-contamination between acoustics and semantics that really plagues older systems. All right, let's look at stage 1. A graph neural network, or GNN, scans the flagged problematic tokens. It then constructs a neighborhood of acoustically plausible candidates. It explicitly restricts the search space to phonetic alternatives by modeling a phoneme-to-word alignment as a graph. So essentially, the GNN just throws out any candidate that doesn't match the acoustic signature of the original audio, no matter how frequently that word might appear in a dictionary. It literally forces the system to prioritize what the word actually sounds like. Next up is stage 2, the masked language model, or MLM. Once the GNN gives us a compact set of words that sound right, the MLM evaluates them. Think of this as a highly efficient, super fast filter. It provides context-aware scoring without the heavy latency of a full generative model. The MLM quickly prunes out candidates that violate local syntactic rules or, say, domain-specific collocations. It just slims down that candidate pool, so only the absolute most viable options are passed forward. Now, notice this single crucial number: 0. This represents the temperature setting, specifically temperature equals 0 or top P equals 1.0. This is the strict deterministic constraint applied to the final stage of the pipeline. Because the candidate pool is already so constrained by the previous two stages, introducing stochastic, random sampling, would just add unnecessary variance in latency. We want a strict deterministic choice here.
And that brings us to stage 3. An instruction-tuned large language model performs the final context-aware re-ranking over those MLM-filtered candidates. Because the LLM is only looking at a tiny, highly constrained list of phonetically and syntactically viable options, it operates within a very, very narrow decision boundary. This brilliantly eliminates the hallucination risks that are usually inherent in open-ended LLM prompts. It safely picks the right word without ever going off the rails into unconstrained generation.
Finally, let's get practical with Section 5, Developer Deployment Guide. If you want to integrate GSpin into your production environment, you really need to treat ASR correction as a constrained search problem. Here are the core engineering patterns: token flagging, phonetic graph construction, two-tier filtering, inference constraints, and fallbacks. This entire containerized post-processing layer is designed to fit right before your intent parser to prevent those cascading downstream failures. Let's elaborate a bit on that first critical step: token flagging. Frankly, it is computationally wasteful to try and fix every single token in an output. Instead, developers should route ASR outputs through a confidence score or NLU parser. You only want to flag tokens that fall below a specific confidence threshold or ones that are actively causing parsing failures. You really have to prioritize those entities, negations, and sentiment words we talked about earlier, and simply ignore the low-impact filler tokens. And here is a vital safety net for developers: fallbacks. What happens if the GNN returns an empty neighborhood, or the MLM filters out literally every candidate? Well, the golden rule here is graceful degradation. You route the token to a dictionary-based fallback, or you simply preserve the original ASR output with a low-confidence flag. The crucial takeaway is that you should never force a correction from an empty or invalid candidate set. Maintain your system stability first and foremost. Which leaves us with a final, slightly provocative thought. GSpin proves that looking at standard global word error rate can totally mask structural, catastrophic errors in your pipeline. To properly monitor your systems now, you need to track token-level WER specifically on critical entities. So, does this framework shift how you'll track your speech-to-text success moving forward? Are you going to make the jump from global WER to critical entity WER? It's definitely something to think about. Thanks for joining me on this explainer, and keep exploring.